Yes. So as I said, that the equation is simple, but involves a lot of back calculations and calculations. Anyways, so as if how to determine this viscosity, you just have to plot a graph of intrinsic viscosity against the molecular weight. Now, you can even convert this into a logarithmic plot also. Log of intrinsic viscosity will give you log of LHS is equal to log of RHS. If you take, you can simplify this. Anyways, I don't have that equation now. It's a simple one. So you get log K plus A log M. So the logarithmic plots will also give you a straight line. Once you have this plot, knowing K and A would be easier. But how would you determine this K and A for unknown samples? For that, you should use other experiments, which are not based on viscometry, based on some other method, principles like light scattering or osmometry, such things. So the K and A are characteristic constants of the given polymer solvent combination at a particular temperature. So they are very sensitive constants. So once you know that, you can use this Markov equation and determine the molecular weight. And this was, of course, the experimental apparatus I was talking of. Fine. But as I told you, the variable here is intrinsic viscosity, but your experiment gives you viscosity of the solution, not intrinsic. So now, for example, you see this. This is a table, a very useful one, which is found in the Gaurikar book textbook. This textbook, Polymer Science from Gaurikar, is a very illustrated one. It has many topics of our syllabus covered in it. Not all, but many topics are covered, and even written in a very student-friendly style. So you can refer to that book if you have one. Now, you see this. These solutions, what you are making, are of varying concentrations, right? Of varying concentrations. See this? Now, for every concentration, you have to calculate the time of flow. The using of viscosity equation is not required here, because I told you relative viscosity can be expressed as T by T naught also, my previous slides. So directly record the time for these solutions. Of course, what is T naught? It's the time of flow for pure solvent, which will anyway be known. If you, for pure solvent, the same T naught is for different concentrations. So do it. As you see, straight away, the relative viscosity is increasing with increasing concentration, right? See here, the relative viscosity is increasing with increasing concentration. And then you have also specific viscosity, which is again increasing. So all viscosities increase. And finally, you have to find out the intrinsic viscosity. Now, intrinsic viscosity is calculated using this formula: specific viscosity divided by concentration. Now you have specific viscosity divided by concentration terms. That will be your intrinsic viscosity. Now convert that intrinsic viscosity into logarithmic function, ln intrinsic viscosity. You have this. You can also do ln n divided by c. And all these values now are plotted against the concentration, of course. But what is the intrinsic viscosity characteristically? I mean, by its definition, when the concentration is tending to 0. So that means what? You get the viscosity value starting from some concentrations of 0.1, maybe the lowest concentration here, 0.1. Goes on increasing like this. Now extrapolate this to concentration 0. So the value of your ordinate intercept will be the value of intrinsic viscosity. Now, after making a table of intrinsic viscosity, you have to take the intrinsic viscosity and plot it in our this principal equation and find out the molecular weight of the sample. So in this way, you can calculate experimentally the average molecular weight of the polymer sample. In fact, all these things what you have discussed theoretically, you are going to do it practically in your lab when maybe your offline classes start. So this is about first method of determining the viscosity of the polymers. In fact, we have 3 or 4 methods like ultracentrifugation and osmometry methods, which we are going to discuss in the next class.